Hi students, in this lecture we are going to solve problems basing on the concepts till now what we have learned. See first one, a progressive wave is traveling in a string as shown. Then which of the following statements about kinetic energy and potential energy of the elements P and Q is true? So given kinetic energy is minimum, potential energy maximum. First take diagram for this one. Right, take a diagram here. This is string. This is now shape of the string. Let us make once again here. That is now shape of the string. And let us mark here. So that yellow line indicates the shape of the string at one state. And point P is here. And point Q is here. So this is a point P and point Q at mean position. So we have to connect now kinetic energy and potential energy. So we have learned that at extreme position, kinetic energy is zero as well as the potential energy, right? So at kinetic energy, at extreme position, kinetic energy is zero, potential energy is also zero. If you remember, while discussing energy, we have discussed very important point that kinetic energy and potential energy, both values are same at each and every time. So at extreme position, both are zero, and at mean position, both are maximum. That means at Q, both are maximum. At P, both are minimum. Now see the options. Right. First option, kinetic energy is minimum and potential energy max. So we are knowing that both are minimum or both are maximum. So option A is not correct. Coming to option B, for point Q, kinetic energy is minimum and potential energy is minimum. So both are minimum, right? And next one, option C, maximum, minimum. Option 4, again, maximum, minimum. Right, I think here we have taken reverse in the diagram. Let us see one second diagram. So we have taken diagram. So this is a point P and this point is Q. Therefore, at P, both are maximum. At Q, both are minimum. So answer is, so at Q, kinetic energy. So at Q, kinetic energy is minimum and potential energy is also minimum because Q is now extreme position. Okay, right. See next problem. Two strings of linear mass densities mu and 9 mu are stretched under same tension. A wave traveling on the latter string towards the heavier string gets partially reflected and transmitted at the junction. Then fraction of instant wave energy getting transmitted to the heavier string is. So it is given traveling from lighter one to heavier one, right? traveling on the lighter string towards the heavier string. So we are given linear mass densities mu and 9 mu. The fraction of instant wave energy getting transmitted to the heavier string is. Right, let us see how to start the problem. First take the data. So it is given that first one, take one more color for next one. And this is the next one. And mu value is given. First one, it is mu. Second one is 9 mu. So this is now junction. So how much energy is now transmitting? The fraction of energy transmitted. Right. So if you want to calculate fraction of energy transmitting, first let us calculate the amplitudes for reflecting wave and transmitting wave. And the expression for amplitude of a reflecting wave. Amplitude of reflecting wave. A reflecting is equal to, here you can see first one mu, second is non mu. That means in first one, suppose velocity v1, second one velocity v2. And we have expression v equal to root of t by mu, right? Suppose v1 equal to v. Then v2 becomes, it is v by 3, right? See carefully. Given under same tension. So tension same. First one it is mu. Second is 9 mu. So v2 becomes v by 3. Now see expression for A reflecting. It is v1 minus v2 by v1 plus v2 into A incident. Okay. That is equal to v1 minus v2. That is 2v by 3. v1 plus v2. 4v by 3 into A incident. And that is equal to A incident by 2. Right. So here we got amplitude of reflecting wave. And coming to energy, it is a proportional to square of amplitude. So here in one important point is, since we are focusing reflecting one, same medium, since medium same speed, right? And mu value same. I am writing here expression for energy equal to, or if you take average value, half mu omega square A square V. When we are taking reflecting one, mu value same, V also same, omega constant. So we can say directly energy proportion to square of amplitude. Now amplitude is becoming half. Therefore, energy of reflecting one becomes 1/4 of instant energy. Right? Therefore, energy of transmitting one is equal to 3/4 of instant energy. Okay. So here we are calculating amplitude for reflecting wave. Now for reflecting wave and instant wave, if you focus same medium, therefore same speed, same mu value, omega constant. So directly we can say energy proportional to square of amplitude. Therefore, a reflecting one is 1/4, transmitting one is 3/4, right? Okay. Now see options. So option is, it is option C, right? Because asking fraction of instant wave energy getting transmitted. If they ask like reflecting, it is 1/4, first option. It is now asking transmitted. So option C, 3/4, right? Now see the next problem. The resultant amplitude due to superposition of two waves, y1 equal to 5 sin omega t minus kx, y2 equal to minus 5 cos omega t minus kx minus 150. So we are given two waves. And if you see carefully, omega t minus kx. And this also omega t minus kx. That means both waves are traveling in same direction. That is along positive x-axis, right? And when we have learned this, we focus that consider their amplitudes as vectors and phase difference between them as angle between the vectors. So let us now focus what is the phase difference here. One is given sine and second is a cos. Let us convert both into sine or both into cos. Okay. Right. See how to convert that. Right. Let us see here. Yeah. First one, y1 equal to 5 sine omega t minus kx. Second one, y2 equal to minus 5 cos omega t minus kx minus 150. So I want to convert this cos also into sine so that we get what is a phase difference. Okay. Right. Let us see how to convert this. This is equal to minus of 5 cos. Wait, we want to take into sine, right? Okay. Let us see. Right. This is now writing into sine. I am writing cos theta as a cos sine of 90 plus theta. This is now sine 90 plus theta. So omega t minus kx minus 150 plus 90 is okay. Writing cos theta as sine 90 plus theta. Sine 90 plus theta means it is in second quadrant, which is positive. Okay, right. And I want to take this minus also inside. So taking minus inside, 5 sine omega t minus kx minus 150 plus 90, writing plus pi. Okay. So I have taken minus inside. So for that I am writing here plus pi. Now see what is the value. So it is equal to 5 sine omega t minus kx. See how much it is. Pi by 2 plus pi. And this is minus 150. So it is now plus 120 means 2 pi by 3, right? Now you can say first one y1 omega t minus kx, y2 omega t minus kx plus 2 pi by 3. So we got now two waves and phase difference is 120. Now this is taken as two vectors, like taking magnitudes as two vectors, right? So their magnitudes are 5 and 5, equal magnitudes. And angle between those vectors is 120, right? I am drawing here. One vector is magnitude is a 5 and one more vector magnitude is again 5, and between those two angle is now 120. Then resultant is, it is a long angular bisector, right? And its magnitude is again 5. Okay, and this angle will be 60. Is a point clear? So we have two vectors of same magnitude 5 and 5, and between those vectors angle is 120. Then resultant will be again same magnitude. It is a long angular bisector, so it makes angle 60. So if they ask now write equation for the resultant wave, then see how to write that equation for the resultant wave. Y equal to y1 plus y2, that is we got magnitude 5, so 5 sine omega t minus kx plus, see angle made by resultant with the first vector is 60, so plus 60. Okay, that is now resultant wave, right? So like this we can solve the problem and see next one. Okay, first see what's the answer given here, right? So it is option here, right? So it is a 5. Okay, right. See next one. A wave pulse traveling on a two-piece string gets partially reflected and partially transmitted at the junction. The reflected wave is inverted in shape as compared to the instant one. If the instant wave has wavelength lambda and the transmitted wave lambda dash, okay. So we have to find relation between lambda and lambda dash. Now see carefully in this key point is a reflected wave is inverted. Inverted means this happens when wave travels from rarer medium to denser medium. I am repeating, wave gets inverted when it travels from rarer medium to denser medium, right? That means speed is now decreasing. Speed is decreasing. So I am writing here. So speed is decreasing. Condition given that take mu1 and mu2. So here, as per the given data, mu2 is greater than mu1 because instant wave like this, and the wave which is reflected, it is inverted. It is inverted. That means it has to travel from rarer medium to denser medium. That's why mu2 greater than mu1, right? That means from this what we can say is V1 is greater than V2, right? So V value is F into lambda. So f into lambda is greater than f into lambda dash. See, frequency is a constant, so frequency gets cancelled. So lambda greater than lambda dash. I am repeating. In the given problem, key point is reflecting wave is inverted. That means traveling from rarer to denser medium. Rarer means V1 is greater than V2, right? V value f into lambda greater than f into lambda dash. Therefore, lambda is greater than lambda dash. Lambda is greater than lambda dash. It is option A, right? Okay. See now next problem. A wave pulse is traveling on a string with a speed v towards the positive x-axis. The shape of the string at t equal to 0 is given by g of x equal to a sin x by a, where a and a are constants. What are the dimensions of a and a? So question 1, it is very simple. Write the equation of the wave for general time if the wave speed is v. Right. So wave pulse traveling on a string with a speed v towards the positive x-axis. Shape of the string at t equal to 0 is a sin x by a. Right. See how to start the problem. A sin x by a, g of x equal to g of x equal to, it is given a sin x by a. This is now shape of the string at time t equal to 0. Okay, coming to the first question, we have to get dimensions of small a and capital A, right? So what we can say here coming to A, coming to the first one, capital A, it is having dimensions of length, right? So it is now dimension is L. Coming to the small a, so whenever you're having sine function, cos function, the inside one must be just a number which has no dimensions. So since x is in meters, a also in meters. Therefore, a also having dimensions of length, right? So a and a both having dimensions of length, right? Now coming to the next one, we have to write wave equation as a function of general time. Okay. Now if you observe, this is just like a sin kx, right? In the place of k 1 by a. I am writing here. In the place of k, it is 1 by a. It is in the form kx. So what I am doing is, the general equation may be like, it may be like g of x equal to a sin kx minus omega t. This is one possibility. So that when t equal to 0, it becomes a sin kx, right? Okay, that means now we have to get what is omega value. Okay, so omega means we know speed equal to omega by k. Already speed is given. That means omega value b into k, and k value 1 by a. That means omega value v by a, right? Now substitute that in this equation. It is A sine kxx by A minus in the place of omega, it is V by A into T. Cross check once. X by A. As usual, in the place of omega, V into K value 1 by A. So omega value is V by A. That is now our answer, right? Right. Now, see next problem. And this also same kind of question. And this question also taken from H.C. Verma. So previous question, question number 9, question number 8. So 8, 9, 10. These three are taken from H.C. Verma. See 10th one. A wave propagates on a string in the positive x direction at a velocity v. The shape of the string at t equal to t naught is given by g of x comma t naught equal to a sine x by a. So same as the previous question, right? Let us see what makes difference here. In the previous question given t equal to 0, it is now t equal to t naught, right? Okay, let us see how to start the problem. A sin x by a at t equal to t naught, right? Condition given that g of x comma t naught at time t naught, it is a sin x by a, right? So this is again of the form sine kx minus omega t, right? So if I am taking here a sine kx minus omega t. If you write t here, then for t naught, it is not 0. See carefully. If you take omega t, suppose I'm taking t only. If you take t equal t naught, it must be x by a, right? So it is not omega into t. It is something else. Then what I'm doing here, writing in the place of this omega into t minus t naught. T minus t naught. Okay. So that if t equal to t naught, this value becomes 0. If t equal to t naught, this value becomes 0. Right? And as usual, just like previous problem, in the place of omega. So we have v equal to v value given, v equal to omega by k. From that omega value, v into k. And we can see the value of k is 1 by a. So it is v by a. Now substitute that in the above equation. In the above equation, it is a sine kx, k value 1 by a minus omega into t minus t naught. So take in the place of omega, it is v by a. Okay, that is now our answer. Right. See next problem. So this is a previous article question. So this is given in 2000, or it is 1990. Very old question, 1990. Given for 2 marks. See the question once. The amplitude of a wave disturbance propagating in the positive x direction is given by y equal to 1 by square of 1 plus x at time t equal to 0 and y equal to 1 upon 1 plus square of x minus 1 at t equal to 2 seconds, where x and y are in meters. Shape of the wave disturbance does not change during the propagation. The velocity of wave is, so when time t equal to 0, 1 by 1 plus x whole square. I think here function is given wrong. Wait, it is actually 1 by 1 plus x square, not whole power. And second one, 1 by 1 plus x minus 1 whole square. See how to solve this one. Right. First one, y equal to 1 upon 1 plus x square when t equal to 0. Next it is y equal to 1 upon 1 plus x minus 1 whole square, right? When time t equal to 2 seconds. Okay. Right. Now from this we have to find what is velocity of the wave. What is velocity of the wave? So whenever a function represents a wave, it should be of the form x minus vt. I am repeating. Whenever a function represents a wave, it must be of the form x minus vt. That means this can be written as 1 upon 1 plus x minus vt whole square, right? So initially t0, vt value 0. Now t value it is 2. So vt value is 1. So I'm writing here. So now vt value is 1. T value 2 seconds. That implies v value 0.5 meter per second, right? So just comparing like that, it should be like x minus vt. So in the place of vt, it is now 1. So t value given 2 seconds. Then we get the value of velocity, right? Okay. See now next problem. And this also a previous IT problem given in 1984 for 2 marks. See the question once. A transverse wave is described by the equation y equal to y naught sine 2 pi into ft minus x by lambda. So it is a transverse wave. The maximum particle velocity is equal to 4 times the wave velocity. See condition. Maximum particle velocity. That means A omega, right? A value is y naught. A omega that is equal to 4 times wave velocity. Wave velocity is omega by k. Right? That is now given condition. So function is given y equal to y naught sine 2 pi into ft minus x by lambda. Right? So maximum particle velocity equal to 4 times wave velocity. See how to solve it. So it is just taking the given condition. First write down the function given. y equal to y naught sine 2 pi into ft minus x by lambda, right? Okay. And condition is maximum particle velocity, e omega, right? A omega is equal to 4 times wave velocity, that is omega by k. This is now given condition. So omega gets cancelled. In the place of it is y naught, that is equal to 4 into, in the place of k. See what we have there. If you take 2 pi inside, y naught sine 2 pi f t minus it is 2 pi x by lambda, right? So in the place of by k value is now 2 pi by lambda. It is a 2 pi by lambda, right? So from this, see what we get condition. So 2 here 2 times. Therefore lambda equal to, it is pi y naught by 2. Okay. Cross check once. Given maximum particle velocity, that is the omega, equal to 4 times of wave velocity, omega by k. Omega cancelled. A value y naught, that is equal to 4 into, in the place of k, 2 pi by lambda, right? Then directly lambda equal to, it is pi y naught by 2, right? See what is the answer? Pi y naught by 2. So it is option B, right? Pi y naught by 2. Okay. See next problem. Okay. And this also previous IT problem given 2001 for 2 marks. Two pulses in a stretched string whose centers are initially 8 centimeters apart are moving towards each other as shown in the figure. The speed of each pulse is 2 centimeters per second. After 2 seconds, the total energy of the pulses will be, so between their peaks, separation is 8 centimeter. Speed of each pulse 2 centimeter per second. After 2 seconds, total energy of the pulses will be given 0, purely kinetic, purely potential, partly kinetic and partly potential. See how to verify this. First take diagram for this one. Diagram for this one is, and one pulse is like this. Now given between their peaks separation equal to 8 centimeter, and both have speed 2 centimeter per second, and this also 2 centimeter per second. In 2 seconds, so in 2 seconds what happens? Each covers 2 into 2, 4 centimeters, right? So each travels a distance of 4 centimeter towards right and towards left. That means now they exactly overlap. I'm making diagram here. Now they exactly overlap. So now this will be like this, exactly overlap. That means when they overlap like this, now string becomes like this. It is simply straight line because now both are cancelling. So string shape is a straight line means there is no potential energy. and all points are at their mean positions. So mean positions means it is a purely kinetic. I am repeating. Since string is now in its natural state, means no elongation. It is now straight line. That means all particles at their mean position. Therefore, total energy will be, it is a purely kinetic. Okay. So our option is now, it is option B, right? Purely kinetic. Okay. Right.